In this test, we'll be looking at the harmonic series. The harmonic series is a very special series such that it's the summation of 1 over k as k equals 1 to infinity. Again, this harmonic series, and again, it's important for us to know the name of this. The harmonic series is a special series that we try and look at very carefully. So the first thing we're going to do is we're going to go ahead through the steps of understanding. First off, it's not a geometric series, so I can't conclude that it's convergent or divergent using that. There's no power of k. It's not a telescoping series. The telescoping concept is that there has to be two terms that I'm adding and subtracting. And yes, in some fractional cases, you can tear apart the denominator based on partial fraction decomp, but this doesn't have two multiplicative pieces in the denominator. So it's not geometric, it's not telescoping. Well, in the last few videos, we learned we could try and attempt the div test. But if I attempt the div test, now I'm going to draw a line here to make sure that this is very clear that I've got two different types of series, and then I've got a div test. So I've got different types of series versus different methods of evaluating series. So let's look at the div test. If I try and apply the div test, the limit as k goes to infinity of 1 over k, well, that's just equal to 0. So the div test fails to give us any new information. Again, it's not geometric, it's not telescoping. It is a harmonic series, so it shouldn't be either one of those. The div test fails to conclude a divergent series, so this doesn't imply that this thing is going to converge in any way. So let's go ahead and fall back then on our good old promising partial fraction decomp, or sorry, partial sums, our limit of partial sums. So I'm going to take the limit as k goes to infinity of s sub k. I'm going to try and evaluate this thing right here. But for me to be able to do that, I'm going to have to create s sub k. I have to create what that formula is for these partial sums. So down here, if I start writing these things out, and I'm not going to take too much time on it, s sub 1 is simply 1. S sub 2 is if I plugged into the series both 1, I get 1 over 1, and I then plug in 2, and I get 1/2, and then I add those two pieces together, so this becomes a 1 plus 1/2. S sub 3 is then going to be 1 plus 1/2 plus 1/3, and then S sub 4, hopefully you guys get the picture, 1/2, 1/3, 1/4. Now as I start adding these values up, I'm going to go ahead and create fractions out of them. This is, just 1. This next one is 3/2. The next one after that is going to be something like 11/6. The one after that is 25 over 12, and we get to a point that these numbers don't seem like they're creating a logical pattern. So I want to know then, what is s sub n if I have 1 plus 1/2 plus 1/3 plus ... all the way up to 1 over n? Is there a pattern that'll work? Or better yet, let's just skip the pattern altogether. You'll notice that this is 1, and then this is 1/2, and then this is 11/6. So it looks like it's increasing, but this is increasing by 1/2, and then from here to here, 11 over 6. That's a little bit more than 1 and, or a little bit less than 1 and 1/2, and this one's a little bit more than 2, and then we're not sure exactly how this pattern is going to continue. So it's a matter of trying to figure out if there is a pattern. And so what we end up doing is we end up starting to come up with this s sub n and say, if n is equal to 1,000, does it look like these values are increasing on forever, or does it look like they taper off? And again, 1, 1/2, little over 2, little over 2. The next one is, again, more than that. If n is 1,000, if I ended up doing this for 1,000 terms, I'd get s sub n is actually approximately equal to something like 7.49. So it does look like it's kind of tapering off, but if I go to n equals 10,000, then I get s sub n is approximately equal to 9.79, again, as I plug in all these numbers. So it appears as though it might be tapering off, but at the same time, if I continue to add in more values, I can just do 10 to the 11th. Let's just jump all the way to there. This is s sub n is equal to approximately 23.60. So it looks like it might be bounded. It looks like it might be tapering off, but I can't be certain with this particular method. And again, we've attempted to use the geometric series. We've attempted to use telescoping series. It's not either one of those series. Again, it has a special name. It's called the harmonic series. The div test failed, and the partial sums seems like it's struggling to come up with a conclusion. So since this isn't working all that well, we have to come up with another method on how to manipulate or work with series. So what we're going to do then is let's go ahead and look at this stuff in a way graphically, and I'm going to kind of hand wave the way through this, and it's not going to be perfect, but it's going to be the best understanding of what we're looking at. So if we start with the basic harmonic series, the harmonic series at term number 1 is a value of 1. So again, s sub 1, if I plug in 1, I get back 1. So I'm going to put up here a value of 1. So this right here is the first point. The second point is at the value of 1/2. Now again, we're plotting the sequences. We're going to start there and we're going to go from that. So if I'm plotting a sub k equals to 1 over k. So my 2 value is going to be 1/2, which is about here, about halfway there. And then my 3 is going to be, again, about 1/3, so it's about, if that's cut into thirds, so right about maybe about here. Now, what we're going to do to help conclude whether or not this series is convergent, we're going to take the concept of, well, what is an integral? An integral is the area under a nice smooth curve. Well, what I'm going to do then is I'm going to say, well, let's ignore a nice smooth curve. If I were to draw a nice smooth curve between all these lines, then yes, I would see that nice smooth curve. And this right here would be the sum of all the terms of this form 1 over k. And it looks like the area under this curve, hey, wait a second. Let me clarify that one more time. The area under this curve would actually be the sum of all values of this form 1 over k for every value in here. So how about, rather than us trying to do this in respect to every individual value, let's just do it logically. So what I'm going to do is I'm going to create myself an overestimate. I'm going to build myself a rectangle for the area of the first value. The area of the first value is 1 unit by 1 unit, and that's going to be 1 over 1 times that height value, 1 unit, the width value. I'm going to do the same thing for this one. Now this one's going to be 1/2 times 1. So the area of this section is 1, the area of this section is 1/2. The area of the next section, if I were to cut across to my value of 4, wouldn't that be, again, my next value of 1/3 right there? And so on and so forth. So I'd have 1/4 and then 1/5 and so on and so forth. So really what I'm trying to do here is I'm actually trying to build the understanding that this value right here, all of these individual terms, if I were to add them all up, it would be an overestimate of the area under this curve. It would be the overestimate of the area under this curve. So in theory, S sub n, the nth partial sum, should be larger than any other integral value from the integral of 1, starting at 1, up to n plus 1, wherever the heck I happen to go for the last term, of this function 1 over x dx. This I can conclude as logical based on the way that I've built these rectangles and based on the way that the partial sum is just these rectangles, while the integral is actually the exact area under that curve, that dotted line that I've drawn. So if I were to work through this, and I'm not going to spend all that much time on evaluating this integral, but the nth partial sum has to be greater than this value, and if I integrate this, I know that it's the natural log of the absolute value of x, such that x goes from 1 to n plus 1, and therefore this becomes equal to, if I plug in n plus 1 and 1, the natural log of 1 is 0, so I get the natural log of the absolute value doesn't matter because I'm working on only positive values. The natural log of n plus 1 has to be, again, in this case, smaller than my s sub n. So my limit as n goes to infinity of s sub n has to be smaller than the ln of n plus 1, specifically as the limit as n goes to infinity. But we can argue right here that the limit as n goes to infinity of this natural log of n plus 1, this thing shoots off to infinity. So if my limit of partial sums has to be larger than infinity, then I have to conclude that none of these values will ever approach a specific number, and the limit as n goes to infinity of the partial sums therefore concludes that the harmonic series is divergent. Again, notice the process in which we did this. We started with the harmonic series, the labeling of this. We just made sure we could clarify what this was. I looked at the geometric series, it was not that. I looked at the telescoping series, it was not that. I attempted the divergence test, that didn't work. I went back to the partial sum statements and I got stuck on just trying to evaluate a pattern. Then what I did was I came up with this concept of looking at the comparison of a sum to an integral. And being able to compare the integral to a sum we can make a number of conclusions. This right here, we have just technically applied what we call the integral test, which is a new method of evaluating a series. There's a couple of details that we kind of hand-waved past in evaluating this thing. The fact that these things are always decreasing, a number of other pieces, but we'll go through that in another video in regards to the integral test. But it's important to note that we have to come up with other methods to evaluate these integrals, or evaluate these series, if we can't do it with the skills that we currently have. And that's what our next steps are, is to come up with methods and ways to determine whether or not a series is convergent or divergent. So no matter what we have, the harmonic series will always be divergent.